While the United States and Canada are still years from switching on their first small modular reactor, China just finished building one, designed to power 500,000 homes. China's new modular reactor is running on Hainan Island, and engineers worldwide are shocked at how fast it happened. Linglong One generates 1 billion kilowatt-hours a year, enough electricity for roughly 1 million people, close to the population of San Jose, California. You heard that right, 1 million people, from a reactor core small enough to transport in modules rather than pour in place over a decade. And that is just the beginning, because the real story is not the electricity. It is who gets to set the global standard for how nuclear power gets built from here forward. Hit a quick like and subscribe so you don't miss the next one. By the end of this video, you will understand exactly why this reactor has other nations scrambling to catch up. Nuclear power has always moved at the pace of caution. That pace just changed. Traditional nuclear power plants earned their dominance the hard way, through decades of proof that nothing else in the energy world can match. A single large reactor can generate roughly 1 gigawatt of continuous power, enough to run a mid-sized city around the clock, without pausing for weather, darkness, or wind. That reliability is not a minor feature. It is the entire reason nuclear plants supply about 70% of France's electricity, keeping the lights on through storms and heat waves that stagger power grids leaning on solar or wind. Engineers love traditional reactors because their output is essentially unshakable once running, delivering the same wattage in January as in July, hour after hour, year after year. Manufacturers love them because a single site produces electricity at massive scale, letting one footprint of concrete and steel replace what would otherwise take dozens of smaller power plants. Governments love them because nuclear plants can run for 60 years or longer on a single license, turning an enormous upfront investment into nearly a lifetime of stable, carbon-free electricity. Here is the part most people never stop to consider. Every large reactor operating today, from Illinois to Guangdong, was built the same fundamental way, poured in place, piece by piece, over years, on a single, unmovable site. Picture pouring the foundation of a skyscraper, then building every floor from scratch on location instead of trucking in prefabricated sections. That is roughly the construction philosophy nuclear power has used since its first commercial plants went online. So why didn't anyone shrink it sooner? Because shrinking a reactor was assumed to mean shrinking its safety margins along with it. And for 70 years, nobody in the industry was willing to make that trade. The physics of nuclear fission does not automatically get safer just because the reactor gets smaller. If anything, cramming the same reaction into a tighter space raises new engineering questions about heat removal and containment that took decades to answer with confidence. That approach has produced some of the safest, longest-running power infrastructure humanity has ever built, but it also means every reactor is essentially a custom-built, one-of-a-kind project, with almost none of the cost savings that come from mass production. But the same caution that built that trust also built something else, a construction process so massive, so slow, and so expensive that it quietly became nuclear power's biggest obstacle to growing at all. Underneath nuclear power's brilliant reliability sits a financial vulnerability that has quietly strangled the industry's growth for 2 decades. This is not about the technology being unsafe. It is about the technology being nearly impossible to finance at the scale the world actually needs. Look at Vogtle Unit 3 and 4 in Georgia, the most recent large reactors built in the United States, which finished roughly 7 years behind schedule and over $16 billion over budget, ballooning past $30 billion total. Enough money to build several entire coal or gas plants instead, a gap wide enough to fund an entire mid-sized country's power grid upgrade. Ontario's newest small modular reactor project tells a similar story before a single unit is even finished. The 4-reactor Darlington plant, expected to power around 300,000 homes once complete, now carries a projected price tag of 20.9 billion Canadian dollars, nearly triple what independent analysts originally estimated was necessary. Those overruns are not isolated accidents. They are the predictable result of building custom, site-specific reactors, where every delay compounds financing costs that keep piling up for years before a single watt of electricity gets sold. The equivalent of paying interest on a mortgage for a house that is not even framed yet. Consider what that does to investor confidence. A project quoted at $7 billion that ends up costing $21 billion does not just cost more money. It makes every future nuclear proposal harder to fund, because lenders now price in the assumption that the estimate itself cannot be trusted. Here is what most people get wrong. The consequence is not just expensive electricity. It is entire countries quietly abandoning nuclear power altogether, not because the physics failed, but because the spreadsheets did. The United States, France, and Canada all saw nuclear construction slow to a crawl for exactly this reason. One bad budget forecast becomes a decade of political hesitation, and a decade of hesitation becomes an aging fleet nobody wants to replace. Which raises the obvious question nobody in the industry wanted to answer for years. What if the entire construction model was the problem, not the reactor itself? In 2021, engineers in China began pouring concrete on an answer that treated the reactor less like a custom monument and more like a product built on an assembly line. The team behind the answer worked for the China National Nuclear Corporation, the state-owned giant that has spent decades building and operating reactors across the country, giving it a manufacturing base most competitors simply do not have. The core idea sounds almost too simple once you hear it. Instead of pouring a reactor's components in place over years, build the major systems as standardized modules in a factory. Then transport and assemble them on site, the way modern bridges are increasingly built from prefabricated sections rather than poured entirely in place. Previous small reactor concepts had been proposed for decades, but most stalled at the design stage. Unable to convince regulators that shrinking the core would not also shrink the safety margins engineers had spent generations perfecting. The new design, called Linglong One, solved that specifically by leaning on passive safety systems that require no human action and no external power to shut the reactor down safely in an emergency. Gravity, natural water circulation, and basic physics do the work instead of pumps and operators. Picture a bathtub that drains itself the moment something goes wrong, with no one needing to pull the plug. That is the essential logic behind passive safety. Remove the human decision point from the most dangerous seconds of an emergency. In 2016, Linglong One became the first small modular reactor design in the world to pass the International Atomic Energy Agency's full safety review, a credential no other SMR design held at the time. Here is the part that changes everything about how nuclear power gets built. Once a design exists as standardized, repeatable modules, the 10th reactor built from that design should cost meaningfully less than the first, the same way the 10th car off an assembly line costs less than a hand-built prototype. That is the entire economic bet behind modular nuclear power. Trade the custom-built inefficiency of pouring every reactor from scratch for the repeatable efficiency of a factory floor. Construction on the actual reactor began on Hainan Island in July of 2021. Using the modular components the design was built around from the start. The question was no longer whether a shrunk-down reactor could theoretically be built safely. It was whether one could actually be built, tested, and switched on in the real world, on a real timeline, under real regulatory scrutiny. Start with the honest number, not the flattering one. Linglong One's commercial operation slipped roughly 216 days past the timeline. China National Nuclear Corporation's own officials publicly gave Reuters in December of 2025 a delay long enough to span nearly 3/4 of a calendar year. An independent tracking of the project shows it costing about 2.5 times more per megawatt than the full-size 1,000 megawatt reactor being built right next to it on the same site. But here is what that number actually means in practice. That full-size neighboring reactor is the 10th or 11th unit of a design China has now built repeatedly for years, meaning its costs already reflect a mature, well-practiced construction process with suppliers, labor crews, and engineering teams that have done this exact job many times before. Linglong One is the very first unit of an entirely new design, meaning its price tag reflects the cost of figuring everything out for the first time. That is the same reason a car's first prototype always costs more than the 1,000th one off the line. The unexpected advantage shows up once you stop comparing Linglong One to a mature full-size reactor and start comparing it to what it can do that a full-size reactor cannot. Get built almost anywhere, including places with weak electrical grids that could never support a traditional gigawatt-scale plant. That flexibility is already proving useful for a non-obvious application most people never think about: powering isolated industrial parks, mining operations, and island grids that were previously stuck choosing between diesel generators and no reliable power at all. Here is the detail that puts everything into perspective. A 1,000 megawatt reactor is often too much power for a small regional grid to safely absorb, the way pouring a fire hose into a drinking glass overwhelms the glass regardless of how good the water is. A 125 megawatt reactor fits grids that size the way a garden hose does, sized appropriately for the demand it actually needs to serve, rather than dwarfing it. The question was no longer whether the first modular reactor could be built cheaply. The question was whether the 10th, 20th, and 50th ones would be, and whether the rest of the world could catch up before China answered that question at scale. The real-world proving ground for Linglong One sits at the Changjiang nuclear power site on Hainan Island, operated by Hainan Nuclear Power Company under CNNC, where the reactor completed its primary circuit cold functional test in October of 2025. The field matched the forecast. That cold functional test checked whether every major system and pipeline in the reactor was properly installed and ready for the next stages, including hot testing, fuel loading, and eventual commercial operation. The kind of methodical, unglamorous milestone that matters far more to engineers than press coverage of switching on a reactor ever does. Construction on the reactor first began in July of 2021, meaning the project has now been under close public tracking for roughly 5 years, through every module delivery and every system test along the way. Field validation matters more than lab results in this industry because a nuclear reactor cannot fail quietly. Every stage of testing exists specifically to catch problems before fuel ever gets loaded, not after. One detail lowered the barrier to future adoption more than any single performance number. Because Linglong One's major components were built as standardized modules rather than custom poured on site, CNNC has already signaled it can replicate the design at other locations with weaker grids without re-engineering the reactor from scratch each time. As one CNNC engineer described the ambition, the reactor was designed to function like a nuclear power bank, compact, portable in concept, and able to deliver steady power wherever it is needed most. The reactor's testing milestones have been documented publicly through CNNC statements and cross-referenced against the International Atomic Energy Agency's own reactor database, giving outside observers an independent way to verify progress rather than relying on state media alone. A level of open tracking that lets skeptics check the claims for themselves rather than take any single source's word for it. If a reactor small enough to ship in pieces surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. It started with one island needing reliable power without a gigawatt-scale plant. Then interest spread outward from there toward remote regions and industrial sites facing the exact same problem. The claim now had receipts. More than 70 gigawatts of new nuclear capacity are now under construction globally, according to the International Energy Agency, and small modular reactors are increasingly the design philosophy driving that build-out. These are not academic citations. These are legal and financial commitments, the kind governments only make when the alternative, falling behind in energy security, becomes politically unacceptable. In the United States, NuScale Power remains the only company with a small modular reactor design approved by the Nuclear Regulatory Commission, though its own flagship Idaho project collapsed in 2023 after cost estimates nearly doubled. In Canada, Ontario Power Generation received construction approval in April of 2025 for the first of 4 GE Vernova Hitachi BWRX 300 reactors at the Darlington site, backed by a projected 20.9 billion Canadian dollars investment across all 4 units, with commercial operation targeted for 2029, years behind Linglong One's timeline, even accounting for its own delays. Russia has already deployed a floating small modular reactor at Pevek in its Arctic north, proving the concept can survive some of the harshest operating conditions on Earth. The regulatory driver accelerating adoption is straightforward. The United States and 24 other countries have formally pledged to triple global nuclear capacity, and modular designs are the only realistic path to hitting that target on any reasonable timeline. Here is what most people get wrong about this race. It was never just about who builds the fastest reactor. It is about who builds the cheapest 10th reactor, because that is the number that determines whether modular nuclear actually scales worldwide or stays a handful of expensive prototypes. In any market where a reactor can be sited on a weak grid without a decade-long custom construction project, a 5-fold reduction in build time is not a curiosity. It is a competitive pressure every energy-hungry nation can no longer afford to ignore. CNNC's testing data remains cross-checked against the IAEA's public reactor database, giving competing nations a documented baseline to measure their own progress against, rather than negotiating in the dark about how far ahead the frontrunner actually is. That transparency is exactly what turned a single island reactor into a genuine global benchmark instead of an unverifiable claim easy for rivals to dismiss. Scale. Modular reactors to even a modest fraction of global electricity demand, and the numbers get enormous fast. If just 500 Linglong scale reactors were deployed worldwide, they could collectively supply power for roughly 260 million homes, a figure larger than the entire population of every country in Europe, combined receiving electricity from units small enough to ship in pieces rather than pour in place over a decade. Even a far more modest rollout, 50 reactors instead of 500, would still represent a meaningful dent in the fossil fuel baseload power that many national grids still depend on today. There is a secondary benefit too, one that rarely makes headlines. Modular reactors sited near where power is actually needed can cut transmission losses that plague electricity carried long distances from massive centralized plants, recovering several percentage points of energy that simply evaporates as heat along traditional power lines today. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. NuScale's own flagship American project collapsed in 2023 when cost estimates nearly doubled, proving that modular design alone does not automatically guarantee affordability. Regulatory certification for new reactor designs in Western markets still routinely takes the better part of a decade, far slower than the manufacturing itself. Linglong One's own 216-day delay shows that even a proven IAEA-approved design is not immune to real-world schedule slippage. Supply chains for factory-built reactor modules remain immature outside China and a handful of other countries, meaning the assembly line advantage does not yet exist everywhere it is promised. And public trust in nuclear power, still shaped by memories of Chernobyl and Fukushima, remains a genuine obstacle in several major markets, regardless of how strong the new safety data looks on paper. Here is the part that puts the whole picture in perspective. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as an engineering one. The researchers and engineers who built Linglong One gave the world a tool. Whether the world picks it up at the speed the energy transition demands is a different question entirely. The story of a reactor small enough to ship in pieces is ultimately the story of what human civilization can build and where it can build it. For most of the nuclear age, reliable carbon-free electricity has belonged almost exclusively to wealthy nations, able to finance gigawatt-scale plants and absorb decade-long construction timelines, while smaller economies and remote regions were left choosing between diesel generators and no reliable grid power at all. A reactor that fits a weak regional grid, ships in factory-built modules, and shuts itself down safely without human intervention changes that math meaningfully. Island nations, mining regions, and countries without existing nuclear infrastructure all become plausible candidates for nuclear power for the first time in the technology's history. What is genuinely new here, not incrementally better, but categorically different, is a reactor built on the logic of a factory floor rather than a custom construction site, where the 10th unit should be dramatically cheaper and faster than the first. That is not a minor improvement. It is a different category of solution to a financing problem that has stalled nuclear construction across the wealthy world for 2 decades. The engineers who built Linglong One gave the world a tool. Whether the world picks it up at the speed the energy transition demands is a separate question, one that belongs to policymakers, investors, and utility operators as much as it belongs to engineers. That is new. And scale is exactly why this matters, more than one reactor on one island. A construction model that gets cheaper with every unit built compounds the way traditional nuclear costs have compounded upward for decades, except in the opposite direction, toward abundance instead of scarcity. If a reactor that generates power without burning anything raises the obvious next question, what happens when the concrete holding up buildings and roads can also store and release energy? That story is worth understanding too, and it is the subject of our next video. China's new energy storing concrete is shocking everyone. The link is in the description. If this changed how you think about the power plant down the road from you, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now I want to hear from you in the comments. Should countries prioritize proven, expensive gigawatt-scale reactors or unproven, cheaper modular ones while the technology is still working out its kinks?